So I'm a physicist. I'm professor of physics in the physics and astronomy department, and I work on the Large Hadron Collider, on one of the larger experiments on the Large Hadron Collider at CERN. So you might have heard about CERN already, but let me remind you that it was founded 70 years ago, and it's the world-leading center for particle physics. It's also a beacon of international and scientific cooperation, collaboration. You might have heard about this concept of a CERN for AI, which is being debated. There's a link there if you want to check out the recent report from the Center for Future Generations. The Large Hadron Collider is the largest and most energetic particle collider ever constructed. It reaches energies which in particle physics parlance are measured in these units called TeV. You can think of a TeV as 10 to the 9, the mass of the proton. It's an underground collider, about 100 meters underground, 27 kilometers in circumference, and Atlas is just across the road from the CERN main entrance at point 1. It's a really large detector, 25 meters in height and length. This is a famous photo from when the original experiment was being installed. We've also upgraded it. We will be upgrading it again in the future. It's also very heavy, about 10,000 tons, and that's a photo of me looking very proud, but a bit embarrassed in front of the detector quite recently when it was being accessible to visits. Just to say a couple of words as to why we want to go to high energies as possible. It's because of the fact that the higher the energy, the smaller the length that you can inspect in this very discontinuous world of ours that we inhabit. So we want to go on the scales of quarks and leptons and gluons and all the very elementary particles that kind of make up all of nature. The up and down quark and the electron are pretty much the only elementary particles that we typically are concerned with, because they make up protons and neutrons and the electron together, atoms and so on. But they are described together with other heavier counterpartners of both the up and down quark and of the electron, and also of the force particles, which are the photon, the gluon, the W and the Z. And then the most recently discovered, and in fact the final kind of constituent of the standard model of particle physics, which is the Higgs boson, which was discovered in 2012, gaining Professor Higgs, late Professor Higgs, and Professors Bru and Angler the Nobel Prize. In fact, Professor Bru had already passed away. Just giving you a crash course in what we do at the Large Hadron Collider. We study the standard model in its most minute details, but we also look for new physics beyond the standard model. For example, dark matter particles. You can think of it as some sort of kind of hidden image of the standard model. We haven't seen any definite signs of beyond the standard model physics, but we've only just started to scratch the surface of what it's accessible at the Large Hadron Collider. So we collide two proton beams head-on, as I said, 14 up to 14 TeV, at the moment 16.5 TeV in the central mass. Thanks to Einstein's very famous equation E equals mc squared, we know that we can produce other particles, some of which might be boring particles that we know everything about, or the Higgs boson, or it could be something more exotic than that. But of course, apples and pears are not what we are looking at, and we look at the primary interaction of protons and in fact their constituents. The red blob is where the primary hard scattering happens, and then lots of particles are produced. They undergo certain processes that we call hadronization, fragmentation and hadronization, and eventually we see the particles that are in fact visible, not visible by eye, by through data analysis in the detector, and we kind of reverse engineer what we see in the detector to go back to what the interaction in the red blob might have been. Someone mentioned this morning triggering we do need to trigger, we use this word trigger to mean that we have to select in real time which data it is possible to keep for further analysis. It would be impossible to keep all of the data because we have interactions at the rate of 40 megahertz, so 40 million events per second. So very fast hardware and software-based algorithm reduce the data so that we enrich the samples in potential signals with respect to the backgrounds, to the standard model events that would possibly mimic the same topology, but not quite be the interesting ones that we want to study. It's the kind of classical problem of a needle in the haystack. We're talking about 1 petabyte per day processed during the LHC Run 2, which concluded in 2018. We are undergoing now data collection in so-called Run 3, which, as you will see in a moment, is even more data and a slightly higher energy. This is a reconstructed event, computer-based reconstructed event. So you might recognize the two photos at the bottom and at the top are the side and front views of the real detector, and you see the same structure in the event display. It's a kind of concentric layers. Each one has a function to measure tracking of particles. We were talking about that this morning, or measuring electromagnetic and hadronic energy from electrons, photons, and protons, and the kind of other members of the hadron family. And then all those lines correspond to trajectories of particles. The rectangles correspond to measurements of energy, or the outermost layer measure the so-called muons, which are the most penetrating particles. The detector has 100 million channels. As I said, 40 million collisions per second. That's a lot of data to think about. And here I'm using this really nice infographics by Luca Clissa. If you have access to the slides that I'm showing, you will find a few links here and there. And this is the link at the bottom of the copyright here. Oh, sorry, of the actual archive paper that I'm mentioning here. A few key numbers in LHC Run 2, which was between 2015 to 2018. We have collected on tape order of 600 petabytes. Ongoing currently the LHC Run 3. By the end of it, order of 4 times as much. When we will eventually reach the higher beam intensity, the higher luminosity of the Large Hadron Collider, from 2029 onwards, we will have more data than that. AI, machine learning, now we call it AI machine learning. In the past, we used to call it BDTs and neural networks. It's been used at the Large Hadron Collider forever. One example that I will wrap up my talk with is kind of BSM models can be kind of a hard beast because it's unknown what we're looking for. And so sometimes, most of the times, we've been performing model-dependent searches where we know what we're looking for, so it is possible to tune our algorithms. But most recently, the experiment is also considering anomaly detection techniques, for example, based on autoencoders, where we trade off breadth and depth of discovery potential. It's a rapidly expanding search, and here is where I stop.
Thank you very much, Antonella. Any questions? Antonella, thank you. It's like challenge Annika now. I'll ask you to pass that.
Thank you for your interesting talk. So CERN has also looked into the application of quantum machine learning for trigger detection kind of selection. Could you comment on sort of the differences between classical and quantum approaches, and if there's any, if you have any thoughts?
So this is a kind of a recent development, and so the idea that you would be using quantum sensors as well as algorithms that are based on kind of quantum computing, but it's not yet part of the bread and butter of what we do. It's being developed primarily for the high-lumi LHC.
Thank you. Any other quick question? Or we could keep on. Oh, yeah.
On the kind of data that you acquire, what types of noise is there intrinsic to the data collection process? So is that which might complicate finding?
So I talked about background. So there's all sorts of backgrounds that are you can divide them into reducible and irreducible. The reducible one would be the ones that are associated with detector features, hot channels, and things like that. So we have to have data quality processing before we actually look at the collision data. And then there is underlying irreducible backgrounds, which are standard model processes that would mimic your signal events. So, and they require different treatments. Some of those backgrounds can be estimated directly from data. For others, we rely on Monte Carlo. I didn't mention that in the data size, we have simulated data of the order 1.5 times what we have in actual life.